A fluid is any matter that has tendency to flow. All liquids and gases are together referred to as fluids. Solids and liquids have a fixed volume, while volume of a gas depends on the volume of its container. However, when an external force acts on certain categories of bodies, their volume changes and the bodies develop a restoring force. The restoring force acting per unit area is called stress. Change in volume due to stress is negligible in solid, very small in liquids, and very large in a gas. Liquids are 10 to the power 5 times less compressible than gases, but are about 10 times more compressible than solids. This is because the molecules in a liquid are not as closely packed as in a solid, but are closer to each other as compared to a gas. Another common physical quantity related to fluids is pressure. Pressure is defined as force exerted per unit area. We experience so many incidents involving pressure in our day-to-day life. One such example is that it is easy to drive a sharp nail into a wall than a blunt one. This is because, for a sharp nail, the area on which force acts is less, hence, more pressure. Here, the force exerted on the nail is perpendicular to the surface on which it is applied. Similarly, the force exerted by a fluid on an object submerged in it is always perpendicular to the object's surface at all points. This is because if there were a force parallel to the surface of the object, then, according to Newton's third law of motion, the object would resist the force in the opposite direction, which would cause motion of the fluid along the surface of the object. However, the fluid is at rest. Since there is no flow of fluid parallel to the surface of the object, we can conclude that the force exerted by the fluid at rest is not parallel but normal to the surface of the object at all points. The normal force exerted by the fluid at a point can be measured by the device as shown in figure. It consists of an evacuated chamber with a spring that is calibrated to measure the force acting on the piston. The inward force exerted by the fluid on the piston is balanced by the outward force due to the compression of the spring, which is measured by this device when placed inside the fluid. Let us now learn how to determine pressure. If F is the magnitude of the normal force acting on the piston of area A, then the average pressure, PAV, is defined as the normal force acting per unit area. In limiting case, that is, if small area of the piston is considered arbitrarily, then the pressure is represented as P is equal to delta F by delta A as delta A approaches to 0. The magnitude of pressure does not change with direction. Hence, pressure is a scalar quantity. Dimensional formula of pressure is the ratio of dimensional formula of force to that of area. Dimensional formula of force is mLT power minus 2. Dimensional formula of area is L power 2. Hence, dimensional formula of pressure is mL power minus 1 T power minus 2. Similarly, the SI unit of pressure is the ratio of SI units of force to that of area, which is Newton per meter square, which is also referred to as Pascal or PA. Pressure is commonly expressed in atmosphere, symbolically written as ATM. Atmosphere is defined as the pressure exerted by the atmosphere at sea level, which is equal to 1.013 multiplied by 10 raised to the power 5 pascals. Another important physical quantity related to fluids is density. Density is represented by Greek letter rho. Density of a substance gives a fair idea of its heaviness. It is defined as mass per unit volume. Density of a fluid of mass m occupying volume v is represented as the ratio of m to v. As mass and volume both are scalars, density is scalar and its dimensions are ml power -3. In SI system, density is measured in kilograms per cubic meter. Density of a liquid is almost considered constant at all pressures, as it is largely incompressible. However, gases exhibit huge variations in the densities at different pressures, as they are compressible. As it is not always possible to remember the density of materials with their true units, generally we refer to relative density. Relative density is the ratio of density of the substance to the density of water at 4 degrees Celsius. For example, relative density of aluminium is 2.7. Relative density is a scalar quantity. It does not have units as it is the ratio of similar quantities and thus it is a dimensionless quantity. The pressure on an object submerged in a liquid is independent of the area of cross-section. Consider a liquid in a cylindrical container. Now, consider a cylindrical element of the liquid with base area A and height h in it. Let mg be the weight of the cylindrical element. Let 1 and 2 be points on the flat surfaces of the element at its top and bottom. The force due to the liquid pressure on the top surface of the fluid element is P1A, acting in the downward direction, while at the bottom it is force P2A acting in the upward direction. Then, since the liquid element is static, the net force acting on the element in the vertically upward direction should be equal to the weight of the element. But the mass of the cylinder is equal to the product of its density, ρ, and its volume, V, or the product of its density, ρ, area of its base, A, and its height, h. Substituting equation 2 in equation 1, we get P2 minus P1 is equal to rho Hg. Thus, the pressure exerted by a liquid column of height h is independent of area of cross-section. The liquid also experiences pressure on its free surface. This pressure exerted by the atmosphere is called atmospheric pressure, is denoted by Pa. If point 1 of the liquid element considered is on the top surface of the liquid and is exposed to the atmosphere, then the pressure at the bottom of the element becomes P equals Pa plus rho Hg, where Pa is atmospheric pressure. Here, the pressure difference, P minus Pa, is called the gauge pressure at that point. This gauge pressure thus depends on the density of the liquid, the height of the liquid column, and the acceleration due to gravity at the given place. Thus, at a given height, the gauge pressure is the same at all points at the horizontal level. Let us consider an activity that confirms this concept. Consider various vessels of different areas of cross-sections connected at the bottom by a horizontal pipe. When a liquid is poured through the opening of a vessel, we observe that the liquid occupies the same level in all the attached containers. The level of liquids, H, in all the containers is the same though they contain different volumes of liquid. This proves that the liquid pressure is the same at all points at the same horizontal level or depth. Similarly, the atmospheric pressure at any point is equal to the weight of a vertical column of air of unit cross-sectional area extending from that point to the top of the Earth's atmosphere. Atmospheric pressure is measured in terms of a vertical column of mercury, whose pressure at its bottom is equal to the atmospheric pressure. The greater the atmospheric pressure, the greater the vertical height of the mercury column. The device used to measure atmospheric pressure is called a barometer. Torricelli devised a mercury barometer. For this barometer, a long glass tube closed at one end is filled with mercury and then inverted into a glass trough containing mercury. The mercury column in the tube falls to some extent and a vacuum is created in the tube. This vacuum is known as the Torricelli vacuum. The height of the level of mercury in the tube is nearly 76 centimeters or 760 millimeters above the free level of mercury in the trough, which is equivalent to 1 atmosphere. There are different units of measurement for atmospheric pressure. It can be measured in millimeters or centimeters of mercury column in the barometer. Or Torricelli's. 1 Torricelli is equal to 1 millimeter of mercury column. or in Newton per square meter or Pascal in SI, or dyne per square centimeter in the CGS system, or in bars. 1 bar is equal to 10 raised to the power of 5 pascals. Another device we use to measure atmospheric pressure is an open tube manometer. It consists of a U-shaped tube, which is filled with a low-density liquid such as oil for measuring small pressure differences, and high-density liquids such as mercury for measuring large pressure differences. One end of the tube is open to the atmosphere, while the other end is connected to the vessel whose pressure is to be measured. The pressure P at point A is equal to pressure at point B, which is P equals PA plus rho Hg, where rho is the density of the liquid, g is the acceleration due to gravity, and h is the manometer height, which is the difference in the height of the liquid in both the limbs of the manometer. Here, the gauge pressure P minus PA is equal to rho Hg. Why is gas not used in a manometer? We know that the pressure is the same at 2 points on the same level on both limbs of the manometer, which contains a fluid. For a given change in pressure, the variation in density of a liquid is negligible, whereas for the same change in pressure, the density of a gas varies a lot. This makes liquids largely incompressible. This is why we use only liquids to measure pressure in a manometer. What happens to an object when it is put in still water? Will it float or will it sink? We can determine this with the help of Archimedes' principle. Archimedes' principle states that when a body is partially or completely immersed in a fluid at rest, the fluid exerts an upward force of buoyancy, which is equal to the weight of the displaced fluid. Consider a very small element of fluid in the form of a right-angled prism, ABCDEF, inside a fluid at rest. As the element is very small, every part of it is considered at the same depth, and hence the effect of gravity is the same at all points of the fluid element. We know that the force exerted by the rest of the fluid on the element is normal to the surface. Let Fa, Fb and Fc be the normal forces acting on the 3 rectangular surfaces of the prismatic element. AA, AB and AC represent the areas of the faces BEFC, ADFC and ADEB of the element respectively. PA, PB and PC represent the pressures acting on the areas AA, AB and AC. Geometrically, in the right-angled triangle ABC, BC is equal to AC cosine theta and AB is equal to AC sine theta. The forces shown are normal to the respective areas that include the sides. Thus, we have FB sine theta is equal to FC and FB cosine theta is equal to FA. Let us call this equation 1. As the thickness of the prismatic element FC is constant, the areas of the three sides of the prism can be expressed in terms of the trigonometric ratios as shown for the forces given by equation 2, which is AB sine theta is equal to AC and AB cosine theta is equal to AA. Dividing equation 1 by equation 2, we get FB divided by AB is equal to FC divided by AC, which is equal to FA divided by AA. However, the ratio of force to area is equal to pressure. Thus, PA is equal to PB, which is equal to PC. Hence, we can conclude that the force against any area within a fluid at rest and under pressure is normal to the area irrespective of the orientation of the area. The pressure exerted at a point by a fluid at rest is equal in all directions. Hence, pressure is a scalar even though it is in the ratio of force, which is in general a vector to area. This is what Blaise Pascal postulated as Pascal's law. Pascal's law states that when external pressure is applied at a point in a fluid contained in a vessel, it is transmitted undiminished and equally in all directions. Let us understand it in detail using an activity. Consider a spherical vessel containing 4 cylindrical tubes A, B, C and D of area of cross-section A, 2A, 3A and 4A. Each of these openings is fitted with an airtight piston. Let piston A be pushed with a force F. Then the pressure on the piston is F by A. Pistons B, C and D move out due to this pressure. However, pistons B, C and D can be held in their position only when the forces applied on them, that is, FB, FC and FD are equal to 2F, 3F and 4F respectively. Then the pressure acting at B, C and D is 2F by 2A, 3F by 3A and 4F by 4A respectively, where each is equal to F by A. This experiment demonstrates that the pressure is transmitted undiminished in all the directions, which proves Pascal's law. A number of devices such as a hydraulic lift, hydraulic press and hydraulic brakes work according to this law. Let us look at each of them in detail. A hydraulic lift is used to lift or support heavy objects. It consists of two cylinders fitted with airtight pistons of varying cross-sectional areas. The two cylinders are connected to each other with a horizontal pipe, where the container is filled with an incompressible liquid. The load to be lifted is placed on the piston of larger cross-sectional area. A2. Let a downward force F1 be applied on the smaller piston A1. According to Pascal's law, this pressure F1 divided by A1 is transmitted equally to the piston, where A1 is the area of cross-section of the smaller piston. As this pressure is transmitted equally to the large piston, the upward force F2 acting on the load is equal to the product of the pressure and area of cross-section of the larger piston A2. As A2 is greater than A1, we have F2 greater than F1. Thus, with a very small force, heavy objects can be lifted using a hydraulic lift. The work done by the smaller force is equal to the work done by the larger force, as the displacement of the smaller piston is greater than that of the larger one. Here, the force F1 applied on the smaller piston is called the effort, and F2, the force required to lift the heavy object, is called the load. By definition, the mechanical advantage of a machine is the ratio of load F2 to effort F1. Substituting F2 with PA2 and F1 with PA1, we get the mechanical advantage as A2 by A1. Hence, we can write the mechanical advantage of a hydraulic lift as the ratio of the cross-sectional area of a larger piston to that of a smaller piston. Let us now study a hydraulic press. A hydraulic press is a mechanical machine used to lift or compress large loads. The schematic representation of a hydraulic press that works on force applied manually is as shown. In this machine, a smaller force applied on a column of liquid is converted into a much larger force acting on the load placed on another column of the liquid, connected to the first column. A hydraulic press consists of two cylinders, C1 and C2, fitted with pistons P1 and P2, and valves V1 and V2 connected with tube T1. Tube T2 connects the cylinder C2 with a water reservoir through a release valve, RV. Piston P2 is a platform at the top of which the substance to be compressed is placed. Piston P1 is raised upwards by the application of force F, at the handle edge of the lever. Upon the action of the handle, the valve V1 opens. The water from the reservoir is sucked into the cylinder C1. During this process, valve V2 remains closed. When piston P1 is pressed down, valve V2 is opened. Valve V1 is closed and the water is pushed from cylinder C1 to cylinder C2 through T1. Due to water pressure, piston P2 moves up, compressing the load between the platform P and the rigid ceiling. To release the pressed substance, the release valve RV is opened to allow the water back to the reservoir. Another device that conforms to Pascal's law is a hydraulic brake used in automotives. A hydraulic brake consists of a master cylinder M, filled with brake oil and provided with an airtight frictionless piston P. Through a lever system, the piston is connected to the brake pedal F. Through a tube T, the master cylinder is connected to a wheel cylinder C, consisting of two pistons P1 and P2, which are connected to brake shoes S1 and S2. The same system is connected to the other wheels of a vehicle. When the brake pedal is pressed, the lever system operates, transferring the force to the piston P. The piston P is pushed inward, increasing the pressure in the master cylinder. According to Pascal's law, this pressure is transmitted to pistons P1 and P2 in the wheel cylinder. These pistons force the brake shoes S1 and S2 to move away from each other, which in turn press against the inner rim of the wheel. Hence, the brake works and retards the motion of the wheel. When the pressure is released, the brake shoes return to their normal positions with the help of a spring mechanism. The study of a fluid in motion is defined as fluid dynamics. For example, consider water flowing from a tap. The water column from the tap is smooth as the water begins to flow out. As the water descends from the tap, its speed increases and it eventually loses the smoothness of the flow. To understand why the smoothness of the flow of the tap water changes, we need to understand the fluid's motion at the particle level. The path taken by a fluid particle in its flow is called its line of flow. The direction of motion of the particle is given by the tangent at that particular point on the line of flow. Fluids can flow steadily or turbulently. The flow of a fluid is said to be steady or laminar if all the particles passing a given point maintain a steady velocity at that point. The velocity of a given particle may vary from one position to another in its path, but at a given point in the path, all the particles passing through the point have the same velocity. Each particle follows the same path taken by a previous particle passing through that point. The path taken by a fluid particle in a steady flow is called a streamline. The motion of the entire fluid can be represented with a number of streamlines showing the direction of flow in different areas. Thus, steady flow is a streamlined flow. As the tangent at a point in the streamline indicates the direction of motion of all the particles at that point, no two streamlines cross each other. Consider an area in a fluid in a steady flow. All the streamlines that are drawn from the periphery of the area constitute a tube for which the chosen area is the cross-section. Such a tube is called the tube of flow. As the streamlines do not intersect, fluids flowing through different tubes of flow do not intermix even though there is no physical partition between them. Fluid dynamics can be better understood taking into consideration the following three factors studied along with the concept of tube flow. They are incompressibility of liquids, rotational aspect of fluids, and viscosity. Liquids are largely considered incompressible when compared to gases, as they don't change volume in response to pressure as gases do. When the fluid flow is along a straight line, it is called irrotational, whereas when the fluid swirls, the fluid is called rotational. The viscosity of a fluid is related to the internal friction when a layer of fluid slips over another layer. In a non-viscous liquid, the effect of friction is neglected. We have learnt earlier that a fluid flowing through a tube of flow does not intermix with the fluid in other tubes. This implies that the total mass of the fluid entering a given tube through any cross-section of the tube in a given time interval is equal to the total mass of the fluid flowing out of the tube from any other cross-section in the same time interval. Consider a tube of flow represented by AB with area of cross-section A1 and A2 at the two ends A and B. Let V1 and V2 be the velocities of the fluid at ends A and B. Consider an incompressible, irrotational, and non-viscous fluid flowing in a streamline flow in the tube. To find the volume of the fluid, VA going into the tube with the velocity V1 through the cross-section A in time delta t, consider a small cylinder of length V1 delta t. The volume of the fluid going into the tube through the cross-section at A is A1 V1 delta t. If ρ is the density of the fluid, the mass of the fluid, Ma, entering the tube at A in time delta t is A1 V1 delta t ρ. Similarly, consider a small cylinder of length V2 delta t at the end B. Then, the volume of the fluid Vb going out of the tube through the cross-section at B in the same time delta t is A2 V2 delta t. Hence, the mass of the fluid, Mb, leaving the tube at B in the same time delta t is A2 V2 delta t ρ. As the fluid is incompressible, its density remains constant. As the mass of the fluid entering is equal to the mass of the fluid leaving the tube, we have A1 V1 delta T rho is equal to A2 V2 delta T rho. On simplification, we get A1 V1 is equal to A2 V2. This expression is called the equation of continuity. If we consider various points in the tube where the velocities of a fluid are different, we can write A1 V1 is equal to A2 V2 is equal to A3 V3 and so on, equal to AN Vn. Thus, we can say AV is constant. The equation of continuity is valid as the product of area of cross-section and speed remain the same at all points of a tube of flow. The equation of continuity represents the conservation of mass in the case of moving fluids. So far, we have considered the laminar flow of fluids. In practical or real-time situations, the flow of fluids is not always laminar. The velocity of a particle at a point in a fluid varies with time. In such a case, the flow of the fluid is called turbulent flow. If the velocity of a particle in a fluid crosses a particular value, called critical velocity, the flow changes from laminar to turbulent. Critical velocity is the velocity of a liquid at which its flow changes from laminar to turbulent. The speed or the direction of the flow varies in turbulent flow. Thus, the motion of water in a waterfall or a fast-flowing river is turbulent. In the case of water flowing out of a tap, the velocity of water increases as it descends. Thus, at a particular point, the velocity of the water crosses its critical velocity and the flow of water changes from laminar to turbulent. All fluids possess energy. This energy is due to variation in the height of a fluid from a reference level and the velocity of flow. There are three types of energy associated with an element of fluid in motion. They are pressure energy, potential energy, and kinetic energy. According to the law of conservation of energy, as the total energy is conserved, the three forms of energy possessed by a liquid are interconvertible. Bernoulli's equation, developed by Swiss physicist Daniel Bernoulli, relates all these three energies. Bernoulli's principle states that for a streamline flow of an ideal liquid, the total energy per unit mass remains constant at every cross-section throughout the flow. Consider an ideal liquid of density ρ flowing steadily through a tapering pipe from its wide end A to its narrow end B. Let H1 and H2 be the height of ends A and B from ground level. Let P1 be the pressure on the liquid, A1 be the area of cross-section, and V1 be the velocity of the liquid at end A. Let P2 be the pressure on the liquid, A2 be the area of cross-section, and V2 be the velocity of the liquid at end B. According to the equation of continuity, the total mass of the liquid going into the tube through any cross-section should be equal to the total mass coming out of the same tube from any other cross-section at the same time. If m is the mass of the liquid element crossing per second through any section of the tube, then A1 V1 is equal to A2 V2. which is equal to the volume of the liquid V flowing per second. This can be expressed as the ratio of mass m to density ρ of the liquid. Let this be equation 1. Since the time considered is 1 second, here V1 and V2 are the length of the liquid element of mass m at ends A and B respectively. Thus, A1V1 and A2V2 represent the volume V of the liquid element at ends A and B respectively. Thus, the work done per second on the liquid element against the force due to pressure at A, which is referred to as pressure energy, is given by P1A1 into V1 is equal to P1V. Let this be equation 2. Similarly, the work done per second on the liquid element against the force due to pressure at B is expressed as P2A2 into V2 is equal to P2V. Let this be equation 3. The difference in the work done on the liquid element in moving from A to B is expressed as P1V minus P2V. Let this be equation 4. This difference in the work done is equal to the total change in the mechanical energy of the element. A part of the change in the mechanical energy is used to increase the potential energy of the liquid element and the remainder to increase its kinetic energy. As the liquid element moves from A to B, the velocity of the element increases from V1 to V2 and the height increases from H1 to H2. Thus, the increase in potential energy of the fluid element per second from A to B is expressed as mgh2 minus mgh1. Let this be equation 5. The increase in kinetic energy per second from A to B is expressed as half mv2 square minus half mv1 square. Let this be equation 6. According to the work energy theorem, work done is the sum of the increase in potential energy and the increase in kinetic energy. Substituting and rearranging the terms, we get the equation as shown. Dividing this equation by m, we get equation 8 as shown. As the ratio of mass m to volume V is equal to density ρ, the equation now becomes P1 by ρ plus GH1 plus half V1 square is equal to P2 by ρ plus GH2 plus half V2 square. This relationship holds good at any point in a streamlined flow. Thus, we can say P by ρ plus GH plus half V square is constant across all points in a streamlined flow. Therefore, the total energy of the fluid, which is the sum of the pressure energy per unit mass, potential energy per unit mass, and kinetic energy per unit mass, remains constant or is conserved across all cross-sections in a streamlined flow. This proves that Bernoulli's principle, holds good for all ideal liquids in a streamlined flow. We can also represent this equation as P plus rho GH plus half rho V square is a constant. Thus, in a streamlined flow of an ideal liquid, the sum of the pressure energy per unit volume, potential energy per unit volume and kinetic energy per unit volume is always a constant at all cross sections of the liquid. Bernoulli's principle, however, has some limitations. Bernoulli's principle is applicable only to ideal fluids, that is, irrotational, incompressible and non-viscous fluids in a streamlined flow. If a fluid is compressible, as is generally the case with gases, volumes do not remain constant and hence density does not remain constant. Thus, we cannot apply Bernoulli's principle to situations such as this. When the liquid is in motion, the viscous drag of the liquid comes into play, which has not been considered while deriving the expression. When the liquid is in motion, some part of the kinetic energy is converted into heat, but it is assumed that there is no loss of kinetic energy. Bernoulli's theorem has a large number of useful applications and is used to explain a wide variety of phenomena for low, viscous and incompressible fluids. According to Bernoulli's equation, the sum of pressure energy per unit mass, potential energy per unit mass and kinetic energy per unit mass of a fluid is constant. Bernoulli's theorem helps us to study the outflow of liquids from open tanks or open channels. The flow of liquids out of open tanks is measured using orifices. The flow from open channels is measured using weirs. A weir is a low dam built across a stream to raise its level or divert its flow. The flow from open channels and tanks is due to gravity, and the change in velocity is due to the change in the pressure head. Here, we will discuss the outflow of liquids from open tanks. A fluid outflow from a tank is known as efflux. Torricelli postulated a law to express the speed of efflux from an open tank, which is identical to that of a freely falling body. According to Torricelli's law, the speed of a liquid coming out through a hole at a depth h below the free surface of the liquid is the same as that of a body dropped freely through height h under gravity. Consider a liquid of density ρ in a tank of large cross-sectional area A1. Let the liquid flow out of the tank through a hole at the bottom of the tank of cross-sectional area A2. Here, A2 is much smaller than A1. Let P0 be the pressure at the liquid's surfaces that are open to the atmosphere, that is, at both the cross-sections of the tank exposed to the atmosphere. Let h be the height of the liquid column above the orifice. V1 and V2 be the velocity of the liquid at the free surface and out of the orifice respectively. According to Bernoulli's theorem, P1 plus half rho V1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho GH2, where P1, V1 and H1 are the pressure, velocity and height of the liquid at position 1 and P2. V2 and H2 are the pressure, velocity and height of the liquid at position 2 respectively. As the liquid is exposed to the atmosphere at both the openings shown at positions 1 and 2, the pressure on the liquid at both positions is equal to atmospheric pressure P0. As the orifice is close to the bottom of the tank, H2 is considered 0 and the height H1 is taken equal to the height H of the liquid column between the orifice and the top level of the liquid. Thus, we arrive at the expression shown. On simplification, we get the expression shown. Let's call this equation 1. According to the equation of continuity, A1V1 is equal to A2V2 or V1 is equal to A2V2 divided by A1. Let's call this equation 2. Substituting equation 2 in equation 1. And simplifying, we get equation 3 as V2 square multiplied by 1 minus the square of A2 by A1 is equal to 2GH. As A2 is much smaller than A1, A2 in the above equation can be neglected and hence the equation changes to V2 square is equal to 2GH or V2 is equal to root 2GH. This represents the speed of a freely falling body, which proves Torricelli's law. The velocity of efflux is maximum when the depth of the orifice is at a maximum vertical distance from the free surface of the liquid, as V is proportional to root H. A venturimeter is used to measure the speed at which an incompressible fluid flows. It was developed by an Italian physicist, G.B. Venturi. A venturimeter is based on Bernoulli's principle. It consists of a tube with a gradually decreasing diameter, which makes a constriction through which the fluid in a pipe is accelerated, followed by a gradually increasing diffuser section that allows the fluid to nearly regain its original pressure head. A manometer in the form of a U-tube is attached to it, with one arm at the wider neck of the tube and the other arm at the narrow point of the constriction. To gauge the speed of flow, the manometer contains a liquid that cannot mix with the liquid flowing through the venturimeter tube. Consider a liquid of density ρ passing through the venturimeter tube with a steady flow. Let ρm be the density of the liquid in the manometer. Consider a point A on the venturimeter tube, where the diameter is larger. Let P1 be the pressure on the liquid. A1 be the area of cross-section and V1 be the velocity of the liquid at A. As the liquid heads for the constriction, the area of the cross-section of the tube decreases and hence its velocity increases, decreasing the pressure therein. This decrease in the pressure at the constriction creates a vacuum and sucks up the liquid in the manometer limb. Therefore, the liquid in the manometer limb connected to the constriction rises. Consider a point B on constriction. Let P2 be the pressure on the liquid, A2 be the area of cross-section, and V2 be the velocity of the liquid at B. According to the equation of continuity, the total mass of the liquid going into the tube through any cross-section in a given time interval should be equal to the total mass coming out of the tube from any other cross-section in the same time interval. Let m be the mass of the liquid element crossing per second through any section of the tube. Since the time considered is 1 second, here V1 and V2 are the length of the liquid element of mass m at positions A and B respectively. Therefore, A1V1 is equal to A2V2, which is equal to the volume of the liquid V flowing per second. As the vertical height of the liquid element flowing through the tube is constant with respect to a reference level, we have H1 equal to H2, and hence Bernoulli's equation takes the form as shown in equation 3. As the velocity V2 is greater than velocity V1, we have pressure P1 greater than pressure P2. We then rearrange the terms in equation 3 to find the difference in pressure at A and B and express it in terms of the density of the liquid and the velocities at the 2 points. From equation 1, A1 by A2 is equal to V2 by V1. Substituting this for the ratio of velocities in equation 4, we get equation 5 as shown. The difference in the pressure at points A and B can be measured as the difference H of the liquid level in the 2 arms of the manometer tube. Thus, the pressure difference is equal to H rho mg. Let this be equation 6. Equations 5 and 6, we get equation 7 as shown. Simplifying equation 7, we get the expression for velocity V1 as shown in equation 8. From equation 2, we get the volume of the liquid flowing per second through the venturimeter at A as equation 9. Simplifying this expression, we get the expression for the volume of the liquid flowing per second through the tube as shown. The principle behind the venturimeter finds many applications. The carburetor of an automobile has a venturi channel or nozzle through which air flows at high speed so that the pressure is lowered. The petrol is sucked up into the chamber to provide the correct mixture of air to fuel, which is required for combustion. Other devices that work on this principle are aspirator pumps and sprayers used to spray insecticides.